This conference will now be recorded.
So this is John Avenson, and this is Passive House Southwest. It's December 1st, 2020. And today's feature is from Build Equinox, who makes conditioned energy recovery ventilators, presented by Ty Newell. Ty, take it away.
Okay, and let me say first, feel free to break in for questions at any time. Please feel free to contact us for any questions, and then I'm really pleased to have so many folks attend this who have CERVs, and so you can let me know what your experience is as we talk about some of these things. I have a balance here in this talk between smart ventilation, and it's not so much meant to be a commercial about the CERV, but about smart ventilation and why it's important, and really the reason why we've developed this technology. And then with the pandemic, to talk more directly about that, some of the characteristics of the pandemic and why smart ventilation, but also ventilation in other buildings, because it's a chain of events that we need to break, but just how they interact. And so I hope between those two sides of it to provide you with some information directly about smart ventilation, but then with current information about what's going on with the pandemic, where we're headed, and what we can do to get back to normal. So here's basically our company. My son Ben, who's president and my boss, and I tell folks I'm not a very good employee. He has to fire me about every other day, but it's just a pleasure working with Ben, and then Alex Long, the other co-owner, who I've known ever since he was a baby. But we're all three mechanical engineers and wired up with this mission in mind. And I think in Aldo Leopold's words, how do we live on a piece of land without spoiling it? That's what drives us. And so I'm talking to you from a 4,500 square foot Morton building, just a typical steel agricultural building, except it's net zero. It's solar powered with 8.5 kilowatts of solar energy. And it's got a geothermal heat pump, also a couple of high efficiency, low temperature mini split heat pumps. And then, as I was just telling John, we just installed a 2,100 gallon rainwater harvesting cistern. And so we do try to hit all aspects of sustainable technology, sustainable living. As far as the CERV and smart ventilation, the key things we're looking for is healthy, good cognition, good sleep, good productivity, basically those things that give us a good sense of well-being as people. And so that's what our goal is with smart ventilation, is to figure out how to keep the indoors healthy. And what I'm going to tell you throughout this talk is that today's standard ventilation, ASHRAE 62.2 for residences, passive house of both flavors, both FEE and FIAS, that these are not adequate levels of fresh air ventilation. And I'll be discussing why that's true. After we talk about smart ventilation, then I want to talk some about guidelines that we've developed at Build Equinox, guidelines that we've been using for a number of years, but that are more important now as it will help stop the spread of this pandemic. And 3 basic guidelines for homes as well as for business, and then three additional guidelines, but simple guidelines, but actionable, quantifiable guidelines that can be used. And then a bit about virus infection transmission, how ultraviolet, for example, and filters, how these impact the movement of contagion within buildings and within our homes. And let me say, if there's one takeaway from this talk, it's that carbon dioxide, that is your best way to know whether or not a building is properly ventilated, whether your home or a public space. And I've been urging people to buy a carbon dioxide meter, take it around with you as restaurants reopen, as you go shopping, and just see what the air quality is. And if it's above 800, don't spend much time in it. If it's at 800 or less, it's a pretty good space and you can feel pretty comfortable with it. But without any knowledge of the fresh air coming in, it's like playing Russian roulette every time you enter a building. And basically this simple chart on the right shows you how the carbon dioxide produced by our respiration is related to the fresh airflow rate into a building. And today's standard ventilation, the rough rule of thumb is about 20 cubic feet per minute per person of airflow. And that would result in about 1,200 parts per million of carbon dioxide. And associated with that level of carbon dioxide is an amount of contagion, whether COVID, the SARS-CoV-2 virus, or influenza, or cold viruses, rhinoviruses, that the amount of contagion you're potentially breathing in is directly related to the CO2 level, because that's telling you how much of the air you're breathing in came from someone else's lungs. And at 800 parts per million, you're getting about 40 cubic feet per minute of fresh air. And that's the level, as we'll see, where you reduce your probability of getting infected if someone is sick in that room. These meters cost about $200. A number of people that have been watching my webinars and discussing these guidelines are buying them. And I'm getting emails, I'm getting text messages, I'm getting photos from folks, and I encourage, if you happen to acquire one and are monitoring places you're going to send it to me. But it's very interesting from, workout places that have 2,000 to 3,000 parts per million that is saying get out of there, or churches, houses of worship, or big box stores, which typically have pretty good air quality. 600 to 800 is pretty typical. It's hard for me to believe just a year ago, as of October, I was in London, and as we've been working on how to reduce the spread of any contagion for years, and that is built into the basis for the CERV technology, that when I was in London, I wanted to go see the Florence Nightingale Museum. I study her work. She was a genius. Her notes on nursing are as true today as they were more than 100 years ago. And her thoughts on this: keep the air as pure as the external air while keeping people comfortable. Airline CEOs keep telling us how you don't get sick on aircraft because they're circulating at 20 air changes per hour. It sounds like a lot, especially when you think of Passive House, which recommends 0.3 air changes per hour. Air changes per hour is a nonsense way to state airflow. Here, this aircraft I was on from Philadelphia to Burlington a couple years ago, and I did catch the flu. It was running at about 20 air changes per hour. That means that I was getting about 12 CFM per person, and I caught the flu on it. So air changes per hour isn't a good metric. So as I mentioned, Where I work is solar powered. Where I live is solar powered. I drive, we've got 2 electric vehicles. I'm pinching myself as I can live on renewable energy and in healthy spaces. So work, this Morton building, this agricultural building, powered with our 2 solar systems, and then my house, also powered by about an 8.5 kilowatt solar array, that we don't sacrifice energy for health, but health is, you want to think beyond energy. The purpose of a building is our health, our security, our comfort, not to save energy. Now here's the problem. You know, homes don't get enough fresh air typically, even leaky homes. It is a myth that a leaky home has good air quality. Where people live and where the leaks are different, and I'll show you some data that demonstrate that. And then air filtration typically is not adequate in a typical home if it happens to have a filter in it. Often it's MERV 8, and that's not going to catch contagion particles as well as the smaller particulates that lodge deep in your lungs and cause a lot of inflammation and health difficulties. And then often homes don't have purification like ultraviolet for sanitizing, further sanitizing contagions. When you do, and this is a balance that we've strived for with CERV technology, with smart ventilation, you bring in an adequate amount of fresh air, and that keeps your brain operating properly. So your cognition, your decision-making, your creativity, your organization of information, that these are kept at peak production levels, that your sleep, that you're getting a good night's sleep, and it also reduces contagion concentration. Air filtration, by moving up to a MERV 13, as we installed in our ventilation systems, and MERV 16, which is equivalent to HEPA in filtration level, this is where you can reduce a significant amount of microbes that may be in the air, as well as very fine particulates. And then if you go the additional step of adding something like ultraviolet at a level which, at the level that we've designed our system to, has a kill efficiency of about 85% for microbes passing through our ductwork, that this relation up top shows how the 3 of these things can factor together and essentially reduce the amount of microbes and reduce the probability that you're going to get sick by a significant amount. So in terms of smart ventilation, there's a variety of things, and it's evolving as we get more and more types of sensors, better and better algorithms for determining inside air quality as well as outside air quality, and smarter ways of doing things. And for example, the unoccupied regions of a house have good fresh air in it that shouldn't be wasted. And when you have one and done type ventilation, what's often too common of a design strategy used, for example, in passive homes, that you simply supply air and pull it out and you don't recirculate it, you build up a lot of particulates. Recirculation is essential to get particulates filtered out, but also recirculation is your opportunity to take fresh air that's been stored in unoccupied areas and make use of it in the occupied areas. And when you don't do that, you end up with rooms that are polluted when they're occupied and rooms that are overventilated that are unoccupied. And so there needs to be a new paradigm on how you not only supply fresh air and supply it smartly, but also then how you distribute it and how you manage it within the home. And it's much more complicated than heating and cooling. And we'll look at the dynamics of that. But you don't have to give up anything. You can have high energy efficiency. And then with the data that you can collect with today's technology, you can use your data to help yourself, and my data can help you and your data can help me collectively as we learn more and more about those things that help us feel better and those things that don't. And that's our overall goal. It's not to be a ventilator. It's how to help each of us feel the best we can and minimize the amount of discomfort, illness, and other afflictions that we may have. And then an overriding thing, it should be unobtrusive. SMART means it should provide you with a peace of mind so that when you enter your home, it's at least one refuge where if you do have respiratory sensitivities, so one place you can enter and know that that air is taken care of. So you're not going to get hit with an asthma attack. You're not going to get hit with some type of allergic response. And that's what we're trying for as well, is to provide a peace of mind. Now, a CERV, and I'm not going to go through in detail all of these parts and components, but it's a very high technology device. The basic unit on the left is about the size, and those of you who have these in your homes, about the size of a clothes dryer. As much as folks in architectural design would like this to be maybe a 6-inch cube, you need much more airflow than what's currently being put into homes, and that's why we have 8-inch ducts rather than 2-inch ducts as some ventilation systems have. And when you get into more complex homes, and this particular unit with this array of wireless sensors and dampers is going into a 10,000 square foot home. And even though it is a large home, it still is just a home for a couple of people. And the challenge as you get into large complex homes is following the people around in a sense and delivering fresh air where they are, because that's where it's getting polluted by their activities, and then conserving the fresh air needed in the unoccupied regions. And so this allows you that capability. But most homes, 2,000 square foot and smaller, and we're in homes anywhere from 500 square feet up to 10,000 or so square feet, that the basic unit for many homes can manage it. Now, while we think beyond energy, that your health is more important, and this should be the primary design consideration in homes, and energy as a constraint. Energy is one of the things to keep in mind as you're developing a healthy home. You can have your cake and eat it too. And for example, this home in Denver that you Colorado folks may be familiar with, this is actually the first home to get a CERV back in 2013. This Illinois passive house home by Tom Bassett-Dilley, a well-known passive house designer who's won many awards with his homes, but we're very pleased to be in many of his homes. First passive house in South Carolina, first passive house in Florida. These are all smart ventilated homes. And then this Vermont home, which we're in probably about 100 of those now. They're all shapes and sizes. They're kind of like building blocks, anywhere from this basic 1,000 square foot module up to 4,000 square foot homes. But these Vermont homes going down to minus 25 Fahrenheit for sustained periods of time. Very detailed study we've done on these that you can download the report from our website. These exceed FEIS and FEE standards by 20%. So very, very energy efficient homes, but all smart ventilated. Just a little bit on health costs. If homes were as efficient as what they should be, and figuring for the U.S. with our 300 or so, 330 million population, that's maybe 100 million or so residences, that would be about 160 billion in energy costs, with roughly half for people activities, hot water, cooking, audio, video, and 80 billion for climate loads, and plus or minus 20%, depending on if you're in a nicer climate or a harsher climate. And that is about 4,000 kilowatt hours per person. And that $160 billion per year for the energy to be comfortable and to do the things we need that we'd like to do in our homes, that compares to current costs for seasonal influenza and colds of about $130 billion a year. Okay, and that's just a couple of simple afflictions that we face every year. And then, of course, COVID's just blown that out of the water with trillions. But asthma, which used to just be 2 to 4% of the populace just a few decades ago, has, for reasons we're still trying to understand, increased to about nearly 10% of our populace as we've immersed ourselves in better sealed buildings with an array of chemicals that we've never been immersed in before, and that's about a $60 billion a year problem. And while we don't understand the chain of events that's causing this increase in asthma and other respiratory sensitivities, we do know that fresh filtered air in homes reduces the amount of asthma attacks, that it will save a significant fraction of this, and potentially making our homes fresher will also reduce the fraction of the populace that's afflicted by this. And then the big dog, which is hard to meter, but the tests that are being conducted now by folks like at Lawrence Berkeley Lab, State University of New York and Syracuse, and Harvard T.H. Chan School of Public Health, is about a $1.5 trillion of value we're losing in human performance degradation by using standard ventilation, ASHRAE 62.2, 62.1 ventilation level. Now, just as what happens if we go from 20 cubic feet per minute per person to about 40, and this is a study by Donald Milton, who you may have seen in, he's regularly on the news, New York Times and CBS and whatever else, because he is the authority on airborne disease transmission. And this study, which was conducted with over 3,000 people working among several dozen buildings, and they looked at sick days among over 3,000 people and the ventilation level, and they found that sick days were reduced by 40% in buildings that had 40 CFM per person or greater, compared to buildings that were at 20 at standard building ventilation levels. And this 40% sick day reduction, that's equivalent to what the flu vaccine effectiveness is. And that's why people are so amazed today with the apparent vaccine effectiveness of the COVID vaccines being 90, 95%. This is miraculous and with such a short time. But a 40% sick day reduction by simply increasing fresh air is about 1 day less of sick day leave out of about 2.5 days per year per employee, and about $500 value. And so, just adding fresh air is as good as a vaccine. And when you compound the two, we get even that much healthier and we save money. Now, let me mention also the cost. And without any energy efficiency, if it's 32 degrees outside, 0 degrees Celsius, and I'm blowing air in at 40 CFM per person rather than 20 CFM per person without any energy recovery, and it's freezing outside and it's 70 degrees inside, that's about 1 penny per hour per person in that building. That's the cost of going from 20 CFM to 40 CFM with it freezing outside. If you're in Vermont, where it's maybe below zero on average in some of their coldest regions, well, that's 2 cents per hour. Is a $25 per hour employee or a $15 per hour employee worth a penny per hour? I think so. So, ASHRAE, my home engineering society, 62.2, the ventilation standard for residences, is called acceptable, but it really is not. It's air quality standard based on tests run in the 1930s, and as many variations as is taken over the year, it still amounts to an odor-based standard, and an odor-based standard in which 20% of the populace is dissatisfied with the air quality. And that's why when you walk into a big box store like a Costco or a Walmart or others, that you'll find most likely that the carbon dioxide level is about 800 parts per million or less. And that's because 20% dissatisfaction with the air quality is not good enough for them. They do not want that many potential shoppers avoiding their store because they think it smells bad. But you cannot smell healthy air, and that's the important point, that healthy air is below our level of odor detection. You cannot smell a contagion. And just to show that smart ventilation works, this is a set point in CERV units, 34 units in Vermont from January to May, and I can guarantee you homes in Vermont are sealed up from that time period. But smart ventilation should not sacrifice air quality when it's cold out, like a number of other ventilators when it gets below freezing because they can't tolerate the frost, that they shut down the airflow, or they turn on a very high energy preheater to save their coil. We don't do that. You need just as much fresh air in the middle of winter as you do in the middle of summer and when it's nice. And this is basically showing that when someone sets their set point, 1,000 parts per million is the most popular, even though we urge people, well, put it down to 800, 850. Here's someone with it at 600. And most homes are dominated by VOCs. That's what kicks in fresh air. But a few homes are dominated, my home for sure, by CO2. And that's an indication that that they're the main source of pollutants. And when VOCs are exceeding the CO2, and not that that's a bad thing. It might be that you're cooking a fair amount. It might be that you have essential oils that make you feel better in your home. So there's other reasons why you may have VOCs in your home, and not all VOCs, some VOCs are healthy. Think of an inhaler for asthma. That is a medication that's a VOC that's helping you feel better. And so, but in any case, most homes are triggered by VOCs and some by CO2, and in any given home, either one can be managed. But definitely smart ventilation keeps your home fresh. This is an exposure plot of pollutants, and ASHRAE allows smart ventilation if it can be shown that it has equivalent exposure or less. And CERVs for sure, when you set the exposure, the CO2 and VOC level, the exposure is less than what you would typically get. Now, these are conventional homes that we monitored over a 2 to 3 week period, about 14 homes, and this is the daily average. And what we call VOC hours, volatile organic compound concentration hours, and CO2 hours, carbon dioxide hours of pollutant exposure, these are like kilowatt hours of electricity. If you use 1 kilowatt of electricity for 1 hour, you've used 1 kilowatt hour of energy. And if in a similar manner, if you're in 1,000 parts per million of CO2 for 2 hours, that's 2 pollutant hours of CO2. And ASHRAE ventilation standards would put you in this yellow band. It's not a fixed standard per person, so it varies quite widely depending on how the house is designed. And some days homes are fine. Usually these are windy days or very unoccupied days. Many days, about half the days, are in this band, and then a few days out here that are, well, very poor air quality. Here's 10 smart ventilated homes spread across several climate zones, but this is January data. So when these homes typically are sealed up unless they happen to be in the south, and you can see that they're largely within this And it also happens that these few data points in January, that January 1st and the following weekend, these were times when homes would have a number of guests visiting. And so a lot of these points aligned with January 1st and January 8th. But in general, these are all within this, people are setting their set points so they get less than 24 pollutant hours per day, which is what we'd recommend. Now let me show you some data from a leaky home, a home that I can't tell you the number of people have said, I live in a leaky home, so it's got fresh air. This is what a leaky home, a 1950s construction home. This one happens to be radiantly heated, so it's not central air in the winter. The home in the main living areas, the family room, living room, when people are there, it gets polluted. Even though it's quite leaky, it hasn't been sealed up at all. It hasn't been retrofitted or renovated. And here's a bedroom that has two young children, 3 years and 5 years old. When they go to bed, it goes zipping up here. And then the parents open the door at about 9 o'clock and it kind of levels off depending on how much they open it. And you can see that their bedroom is quite high. And basically this means if one of the children are sick, the other one's going to get sick. So leaky homes do not have good air quality. And we see this time and time again. Well, what about a certified passive house that is set up with high efficiency HRV? It's set up to building ventilation standards, ASHRAE 62.2 or passive house 0.3 air changes per hour. Well, this home, which has two people in about a 2,000 square foot home, when those two people are home, the main living area is polluted. And then when they went away for about a week, week and a half, their son was checking on the home. That's these blips that you see. It's overventilated. And then they came back home and it's polluted again, whether by VOCs, the blue line, or CO2. Now here's a similar size home with CERV smart ventilation. And the green bars are showing when active ventilation occurred because it hit this threshold. And this is my house, Equinox house. I have it set at 850 parts per million. And so you can see where it would trigger either on CO2 or VOCs. The VOCs are typically indicating some of my spouse's wonderful cooking aromas. And chicken noodle soup, I think that's a healthy VOC. Now, as I mentioned, recirculation is essential in all homes because most particulates in homes, from shedding skin to abrasion of textiles and the soles of your feet and cooking particulates, most particulates are generated indoors, and recirculation is how you have an opportunity to filter out those particulates as well as make use of stored fresh air in other areas of the home. And as a rule of thumb, a CERV will manage the air quality of a home without additional dampers and distributed sensors if it can turn the home over in 1 to 2 hours. And basically a 2,000 square foot home with typical ceiling heights, 8-9 feet high, will turn that home over in 80 minutes with about 200 CFM, which is our typical airflow rate. And that will make use of this and keep particulate levels low. And here's Equinox house with a couple of days of air quality measured in the master bedroom and measured in an unoccupied bedroom and then in the main room. And you can see the complexity of the air quality in that. Now what the CERV sees is a mixture of air coming from these rooms, and that's the yellow line. And when it hit 850, it triggered ventilation, and you can see it getting dropped down. It drops down 100 parts per million, and then it stays below that, and when it hits that threshold again, it goes back to fresh air ventilation, brings it back down, and then If it doesn't hit that, you can see the rooms depending on, here's nighttime where the master bedroom is a higher level than the main room. And then other times the main room is higher. But it's very complex, much more complex than heating and cooling. And that's why there's quite a bit of computational power built into our controls. And that's why we also have the capability to control other types of comfort systems. Geothermal heat pump systems, mini split heat pump systems are some of them, but we also control like radiant floor heating systems. Now, when you do get to a more complex home, zone control then is an option. And to just give you a simple idea of that, you can layer on an array of wireless and wired sensors. For example, a CO2 sensor that can detect locally whether this zone has pollutant levels that should be addressed while this one zone doesn't, or an occupancy sensor, or a switch sensor that, or a switch. You flip a switch and it tells the CERV, ventilate with fresh air for 15 minutes, 30 minutes, or a circuit sensor that if you flip, say, a light switch, or you turn on the fan for your kitchen ventilation hood, that this automatically detects a current flow in that circuit, tells the CERV, sending out a local wireless signal to go into fresh air ventilation mode. And what the CERV can do then is to open a damper to this area while closing, but not fully closing. We close partially because we don't want to stagnate any space in the home, but basically favoring this area for fresh air supply and potentially exhaust or return dampers. And these are what some of those sensors look like. The new temperature humidity sensor, where this one's about the size of, I hate to use a pack of cigarettes as an example, but say the size of a calculator or a pack of cigarettes. But now it's about the size of a doorbell. Battery free. We use the N-Ocean protocol, similar to a Zigbee or a Bluetooth, but this is a very powerful wireless that often is powered by ambient. In the case of this switch, battery free, it's your thumb power that powers it. A solar sensor in the case of this temperature, carbon dioxide, humidity sensor, or these current sensors that when you flip a switch can detect that somebody's in that space. And as I mentioned, this example for a kitchen, if somebody switches on the vent hood, this circuit sensor can tell this damper to close down maybe the ventilation from this area, so it emphasizes kitchen ventilation. Now, I see that we're coming up on an hour. We started a little bit late, and I want to talk some about reopening guidelines, but then I'll move through some of these fairly quickly. But I just want to give you a sense of how all of this works together, because it's great that we are safer in our homes with something like CERV Smart Ventilation, but it doesn't do us any good if other places that we're visiting, that we need to visit, or where we have to work, if those aren't safe. So we have 6 simple guidelines, quantifiable guidelines, and you can read these from an article we posted in May, well before CDC and others acknowledged that this is an airborne disease. We knew it was because we've been working in this for years. And these guidelines are no different than the guidelines we've been specifying to people for years. But these guidelines amount to the following. As I mentioned previously, 800 parts per million or less is a level that reduces the probability you're going to get sick if there's someone infectious in that space, whether with the flu or with the SARS-CoV-2 virus. And then recirculate air through a MERV 13 or better filter, and this will remove up to 90% of virus-laden contagion particles. And then think about adding ultraviolet germicidal irradiation. an excellent webinar by Bill Bonfleth, a professor at Penn State University and former ASHRAE president, but also a world-renowned expert in UVGI. His webinar is available free online, but basically at about 4 watts of electric power per person, or about 16 watts of electric UVC bulb is about 4 watts of UV power, and for about 200 CFM of airflow rate, that will give you about an 85% kill efficiency of a virus. Viruses, molds, bacteria, they all have different levels of UV needed for killing them. Molds and fungi are, as larger particles, a little more difficult, but all of these can be managed through all three of these methods. On top of that, in public gathering spaces, ultraviolet germicidal irradiation for sanitizing surfaces are done in medical facilities, looking at expanding this into our restaurants, into our public shopping spaces and other public gathering spaces. This has been shown to add an additional significant level of sanitizing surfaces above and beyond that of washing with a disinfectant. And have staff, customers wear masks, and then stay much more than 6 feet away from anyone not wearing a mask. And as I'm undergoing a test, and you can see my my pandemic beard and hair growth, I don't like testing, I don't like face masks, but they are critical. Now the CDC acknowledges airborne, and what they're finally acknowledging is that when you cough or sneeze, there's this contiguous cloud, this homogeneous cloud that doesn't just diffuse as it gets away from you, but it moves 20 to 30 feet. And if you're down an aisle in a store and someone sneeze or cough clouds moves past your head, you're going to get a very concentrated amount of contagion, as well as the aerosol concentration from your respiration building up when you don't have proper fresh air ventilation and filtration. And so droplets are important to stay away from. Face masks help move and take care of a number of those. But these very small droplets that come from our respiration, they don't get rid of those as effectively. Here's a test that we conducted at the University of Illinois just a month ago. It was getting quite cold for listening to jazz, and even though your beer stays cold when it's 45 degrees outside, the musicians as well as us in the audience, it's not a very satisfying experience. So moving indoors, we conducted a test at this venue in Urbana. My colleagues in environmental engineering brought in their instruments to measure particulate size, particulate mass, carbon dioxide, and volatile organic compounds. We had 2 U of I jazz ensembles play, and we had about 25 people in this COVID-free atmosphere. And how do we know it's COVID-free? Well, we're very fortunate that the University of Illinois has an extensive testing program that's more extensive than anywhere else that I'm aware of in the world. We test twice a week. We have rapid testing. On your phone, you receive a message within the same day, within a few hours, that you're negative, hopefully. And so we could take a group of COVID-free people, put them in this venue, and unfortunately, we wanted to repeat that, but as we've undergone a surge, as you have in other areas of the U.S., that we've had to delay that to see that we can recreate this data. But we have what's called the pig pen effect, our own personal pollutant cloud. And part of that cloud is made up of 0.3 micron particles. Some of these are just kind of a debris cloud that's following us around as we off-gas things that turn into very fine particulates. A human hair is 100 microns in diameter, so 0.3 microns is very tiny. It gets deep in your lungs. And you can see that at about 3 o'clock when we started this experiment, carbon dioxide increased. We were not ventilating the space, and people were increasing these stars, and also very small particulates increased. And this is the pig pen effect. And basically at this 8,000 particulates per cubic meter of these very fine particles, that means we're inhaling about 64 million of these things per minute. And it's an amazing number. But that's only a microgram, and a microgram is 1,000th of a milligram, which is 100th of an aspirin. So it's not a large amount of mass. And then some fraction of this are very fine respiratory droplets coming out of us. When we turn fresh air on, you can see CO2 dropped. CO2 was at a fairly high level. We weren't ventilating, but it dropped. And you can see the very fine particulates dropped, as we've said they would from our modeling. And then we turned the fresh air off, and CO2 started to build back up. We had about 24, 25 people in there. But we turned on a recirculating filter with a MERV 13 filter. And you can see the particulates continued to drop until it hit this base level. And so both of those guidelines, fresh air and filtration, removes particulates effectively, and both are important. As far as this chain of transmission, a study performed where they investigated several thousand people that had been infected, and they sorted them into people where they could follow the infection and define what they called outbreaks, where 2 or more people were infected by an infectious person. And for the 1,000 to 2,000 outbreaks that they studied, 20% of those occurred in some public gathering space, a store, a restaurant, a party, a Rose Garden party at the White House perhaps. And in those, even though that was the minority of the outbreaks, 8 to 10 people were infected with this 20% of outbreaks. The other 80% happened at home, where 2 to 4 people were infected. So basically, a super spreader and shedder goes to this public space, spreads contagion around, a large number of people, 8 to 10, get infected. They go home and they infect perhaps some gray-haired person like me when my hair grows back in, as well as others. And that's how you have one person infecting 30, 40, or more people. Now, a super spreader and shedder, just to give you a little idea on that, when we talk about droplets, there's the droplets that come from this region, your trachea, your bronchial tubes, your sinus, and when you sneeze, cough, talk loudly, yelling, that's what the mask is largely catching, those bigger droplets. And then some people have a characteristic where really fine droplets, 0.3, 0.5 micron in size, coming from deep within your lungs, just as a natural result of your breathing. And these can make it through at least today's mask. A better mask, a MERV 13 equivalent, MERV 16 equivalent, what we call an N95 mask that should be more plentifully available, could help stop. But these are making it through the mask. And it turns out that roughly a quarter of the populace is responsible for most of these droplets. But you can't tell which among us are emitting these very tiny invisible droplets that you cannot see at all. They're almost the size of large molecules. And so these droplets coming out, you can't tell who is going to release them. Half of us don't release any. It's just a characteristic of your lungs. It doesn't matter if you're sick or not. These droplets just happen to come out of some people deep in their lungs. And then only a fraction of people who have the virus shed it. Sometimes the virus is lodged in other areas. If it's deep in your lungs, And if it also tends to be a person that tends to shed, then between somebody that releases a lot of droplets of this nature and that there's a viral component, these are the ones that are super spreaders. But we can't tell who is, so we have to protect all of ourselves. We have to think of others. Now I'm going to speed it up because I know I'll be way over time. So I just want to say there's models. This is what's called the Wells-Riley model for predicting the probability you're going to get sick. If there's one sick person who's infectious and 3 who are uninfected, the amount of time you spend, so if you're at 800 parts per million for an hour, 2, 3, 8, the probability you're going to get sick depends on that. ASHRAE ventilation, passive house ventilation puts you in this range. So if you're 8 hours with somebody that's infectious, that's being ventilated by ASHRAE standards or passive house, you're going to get sick. If you're in a home that is ventilating at about 800 parts per million, well, it's still pretty high, but when you match the other things we've said to do, so this is looking at the time and recasting that same plot. Here's 2 ASHRAE standards from 2010, which was a bit lower airflow rate than ASHRAE's 2019 standards, and then passive house. And here's the nominal 20 cubic feet per minute of fresh air per person. And then here's going to 40 CFM. And here's adding filtration through a MERV 13 or better filter. And then here's adding ultraviolet sanitation. So going from essentially a sure thing that you're going to get sick in an 8-hour period with someone that's infectious to getting down to 50%. And then the other set of guidelines, if you wear a mask, well, that helps a bit here, but you're still pretty much going to get sick in 8 hours wearing a mask under standard ventilation conditions compared to about 30% if you double the ventilation, filter and recirculate and filter, and then use ultraviolet sanitation. And 30% probability of getting sick after over 8 hours is a lot better than 95%. Okay. Now, I'm not going to talk in detail about this, but this is actual data, carbon dioxide data of an actual business, 120 employees, 25,000 square feet, $90,000 utility bill, and that's a pretty big utility bill, but it had computer servers in it, so a pretty large electrical load, and $6 million payroll. This is what you need to be concerned about. A sick day of this per employee is $60,000. You double the ventilation to this building, you're going to save this much money, and that's pretty sizable. But the bigger savings is productivity is going to increase by 10%. That's about this much. That's 10 times the utility cost. So as much as a facilities manager is saying, no, you can't double that ventilation, my utility budget's going to skyrocket. Well, in this particular building, since we had the energy budget and did the energy modeling, it actually was going to decrease a little bit by doing this smart ventilation of the building. And so you need to look at the details of it. You can't just shoot from the hip. Here's a house of worship, Sunday. This is a high enough CO2 concentration, you're going to get sick in an hour. And that's why churches, mosques, temples are super spreader events. Here's a boarding bridge. The aircraft themselves, 20 air changes per hour, that's not enough. That's about 12 CFM per person. So as much as that sounds like a lot compared to 0.3 ACH for passive house, that's not a lot. And so you can still get sick if there's an infectious person around you on an aircraft, regardless of what airline CEOs say. But the boarding bridge, and we started a company that built these big air conditioner, fresh air ventilators. These are 60-ton, 120-ton air conditioning heat pump machines. these big yellow ducts. The rate that we blow air in keeps the aircraft fresh, but the boarding bridge gets insufficient air. Here's deplaning, here's boarding. Boarding is where, when it's a cattle car filled with people, you're going to get sick. So unless you're able to fly first class, hang back, let it clear out a bit, then get on. Here's the Department of Motor Vehicles that we monitored. It has demand controlled ventilation, smart ventilation, except they need to set this down to about 800 to keep their employees safe over an 8-hour period. You're okay going in with this level of CO2 for an hour or so that it takes to renew your license, but the people working there are not. And I won't talk in detail, but here's an office, a demonstration office we built at the University of Illinois. Set your CO2 level, set your VOC level, set your comfort. You're the happiest person in the world, unlike 80% of people who are unhappy with comfort and air quality in the places they work. And as I mentioned, a penny per hour to double your ventilation without any energy recovery technology. Filters, similarly, as people resist going from MERV 8 to MERV 13 filters, oh, our fans can't handle it. Well, actually, a more resistive filter is easier on a fan than a less resistive filter. So it's a myth to say the fan's going to be overworked, it's going to burn up. It will not. But let me also say, it's a myth that a MERV 8 filter has lower pressure drop than a MERV 13 filter. A California Energy Commission study demonstrated this. It's really the quality of the filler you buy. It's the material, the pleating. It's the design of that filter that determines pressure drop. And they found just as many MERV 8 filters that had as high of a pressure drop as MERV 13s and vice versa. The cost will be more, of course, but you add up the cost for this particular filter that I just looked up on Amazon, and for the type of airflow rate you'd run through that. And just for the amount of airflow, 40 cubic feet per minute for 21 people that a filter this size could address, you're talking fractions of a penny per hour for the filter costs and for the power costs. Okay, it's nothing compared to the wage or the value of the human being. And ultraviolet in a similar manner, and thanks to John for this pretty picture, but the ultraviolet that we integrate into a CERV, when you look at that cost per hour of running that continuously, it comes down to about $1 per, or a penny per hour. And for sure, you're worth it. So let me end on this. As I mentioned, we don't think of ourselves as a ventilator company. We don't think of ourselves in terms of like a bathroom ventilator or an exhaust ventilator. Our focus is our health, our well-being, and our comfort. And this is a concept we call pre-ventilation or preventilation. And what preventilation means to us and where we're going is that this day and age of big data and artificial intelligence, as you know, and we need to be distrustful. We can't trust that people are going to do good things with this. The smart grid, is it smart for the utility or smart for us? We need to be on guard. But the data from how much time we spend on a computer or watching a screen to how much time we operate a vehicle, our nutrition, our exercise activity, the outdoor environmental reports, the data collected by the CERV, we know that as we use artificial intelligence combined with the fusion of all this data, we can help ourselves feel better. We can perhaps see that we're on a path where in a day or 2 or 3, we might be headed toward an asthma attack or a migraine headache or a bout of depression or some other affliction that if we change the course of action, we get out for an extra walk, we change our diet, that perhaps we can mitigate or even avoid that bout and maybe sleep better. This is what we want to do with the technology and where we're going. So I'll end on air quality. It's complex to manage it. It's much greater value than the cost of energy, but it's difficult because we don't meter it. And smart ventilation should give people the peace of mind that their air quality is automatically managed. And then simple guidelines. If you can get a carbon dioxide sensor, start mapping places out and just see how good the air quality is. Filter it, recirculate it. If you don't have recirculation built into your home, just get a space recirculating filter, or build your own with a box fan and a couple of MERV 13, MERV 16 filters. And ultraviolet is an additional layer these times of COVID to get another level of sanitation and microbe reduction. And we understand this COVID-2 disease. You can find a number of papers I've written on predicting the disease transmission, as well as other aspects of it. You can find those in our newsletter articles and on some citations from those. But thank you very much for attending. I want to say there's some references here that you can find at the end of this, and I think that these slides will be available for you to take a look at as well. So with that, I'll turn it back to John and be glad to answer any questions that you may have.
Thank you, Ty. And I just want to remind, if you internet your CERV-2, then you can see these graphs for yourself at your own home or on your phone, right?
I hope so, yeah. But let me know if you can. And John, feel free to post this presentation too, so people have direct access.
Yeah, this is recorded, and it'll ultimately be posted on the Passive House FIAS.org website. And some of Norbert's CERV-2s are on the internet, and also my house, and it's fun to watch the levels pass by the trigger level. The CERV comes on and brings it back down to 800 or whatever.
Yeah, I mean, it's a very dynamic situation. I'm assuming in your house, every time you fire up the popcorn machine, it might be bringing in some ventilation. But popcorn's well worth it.
Yep, oil and heat do a big thing. Also cats. Any questions from the audience?
Yes, I've got a question. My name is Hank Keating. I'm in Massachusetts. I'm the president of Passive House Massachusetts, and I've been involved with Passive House for a dozen years now. I'm speaking to you from my Passive House. And I've always had an underlying suspicion that our Passive House ventilation rates were probably too low. And you're the first person I've heard actually just state it outright that they are. Mm-hmm. And it sounds like you're suggesting that they are low by 100%. Instead of 20, it should be at 40 CFM per person. How does that work in terms of the energy budget? Is that going to cause a problem with the Passive House calculations for the energy budget? And the second part of the question is the CERV-2 certified as a Passive House piece of equipment by FIAS or FEE?
Yeah, so thank you for the question, Hank. And, and we work with Passive House a lot and have for, well, our very first presentation on the concept of the CERV was in 2008 at the third Passive House meeting up in Duluth, Minnesota. So we're great believers in Passive House technology, and that Passive House has educated a lot of people in how to design very, very energy efficient homes. And we know on both sides of FEE and FIAS, a lot of people, and they've heard this from us, from Wolfgang Weiss to Katrine Klingenberg for many years. So we're not certified because it's hard to figure out how to certify us, because with smart ventilation, and this is where HVI and others who do like ERV and HRV, so the Heating Ventilation Institute, they're focused on an energy standard instead of a health standard. And what we want to see is a ventilation standard in which you take a space, you pollute it, and look at how that system, whether it's active or passive, manages that, and then have a metric, an exposure metric of so many CO2 pollutant hours per time, as well as an energy metric on how well it did with whatever type of outside environment it's dealing with. And so the way you gain most of your energy efficiency with smart ventilation is by only ventilating when people are there. And so if you think of using 40 CFM per person when the house needs it, and then not when they're not home, there's a big savings there. And on top of it, getting air from the unoccupied parts of the home over to the occupied, which delays and reduces the amount of fresh air ventilation that you need. And then by sensing directly the CO2 VOC levels, and as particulate sensors get to a level that that we can trust, and currently all particulate sensors, yeah, they're interesting, but it's a $10,000 instrument to do that properly and to keep calibrated. And today's particulate sensors that you're seeing in home monitoring, they're maybe good for the 90-day or 1 year warranty period, but certainly they're not at a level that you're going to put in something that's got a 5-year warranty or more. But that's why you gain a lot of energy efficiency. And in our case, through a heat pump, we also do an exchange of efficiency, but it's not a simple number to generate. And so while the urge is to try to generate a single number of efficiency, when you're in Vermont and it's minus 25, and I've visited homes in Vermont when it was below minus 20 in the middle of winter with 2 feet of snow on the ground, and visited, you know, a few dozen of our project homes. Standard ventilators are either going to reduce the outdoor airflow and be polluted, or they're going to kick on about a 800-watt pre-electric heater, which just destroys its energy efficiency, but it's not included in the rating. So we're in active discussions with Passive House folks, and we're very friendly, even though I'm critical of the amount of airflow. And I know with FIAS, with their new standards that they're currently having reviewed, I plan to put in some comments to that effect, because we can do better. And as I mentioned, if you just simply bring in 32-degree air at 40 CFM versus 20 CFM without any energy recovery, you're talking about 1 penny per hour difference to condition that air as far as its energy cost. So it's not a big cost, and it's definitely not a dominant, say, energy amount to get, especially for the cognition improvement, the sleep improvement, and the reduction of sick days, the reduction of illness.
Okay, so you're not a pre-certified piece of equipment, which is fine.
No, so they always have, yeah.
But are people getting FIAS or FEE certification with a CERV-2?
Oh yeah, yeah. They assign a minimum energy recovery efficiency, which I think had been about 70%, but I think for FIAS, the current release, it's now like 66% as far as energy recovery ventilation efficiency that's required for certification. But basically, because of the unknown nature of us as far as how to put a single number on something that's actively managing the air, They do that. And so we're in many, many passive houses of different flavors, multifamily, single residences.
Great, thank you.
Mhm.
This is Larry. Can I have a quick question? Have you done any work with air-to-air heat exchangers in conjunction with your device and sensors?
Yes, we've examined those, and in our early days of going through various design iterations of having an ERV or not having an ERV, for example, a heat exchanger core, we just found that it didn't add anything beneficial to our heat pump technology. And so our heat pump is a very efficient heat pump. It's an inverter drive, it's digital controlled valves, and as I mentioned, our DNA is in designing heat pump systems, very, very efficient heat pump systems for like automotive, for aircraft, conditioning, things of that nature, and refrigerator appliances. So our background say CERV was doing prototyping and concept design for companies you've heard of around the world that make appliances, automotive air conditioners, and the like. And so as we looked at that, we really saw the heat exchanger core as a weakness for a number of reasons. First, you really can't tolerate much moisture, and if that moisture freezes, you destroy the core. And then we don't like having a polymer in there. To us, having a polymer type heat exchanger, whether it's a polystyrene in the case of some or a cellulosic type wall material, to us, it's like blowing air through a box of styrofoam peanuts. And so we like blowing through metal heat exchangers, and we could get the energy recovery that we needed through our heat pump technology. And then also, because our heat exchangers are frost, we like frost. We like freezing on our coils because that condensation of water vapor on a cold winter day when we're pulling air out of the house and it's freezing on our coil, we're pulling heat out of that moisture that came out of the house, and that's part of what we're adding to the sensible heating, to the fresh air that's coming into your house. And we like that route. And then if you want to add moisture later on in the house, you can do that, as opposed to trying to recirculate some of that moisture through a semi-permeable membrane. But most homes, as we see, when they're smart ventilated, and you can see this online. If you go to our website and on the homepage where it says take control, you can see live data from the past, well, you can see historical data over the past 5 years from my house, and go to the dead of winter, and you'll see that our house stays 40, 50% relative humidity throughout the middle of winter without any moisture addition.
Cool. What's the URL for your website?
BuildEquinox.com.
Okay.
Just on it, yeah. And then from that homepage, just scroll down to where it says take control and touch that, and you'll see a live screen, control screen for our house. And you can go to all the settings on it, temperature settings, CO2, VOC settings, and hopefully you're not able to hack into it and actually change the settings, but it lets you at least pretend you're changing the settings. And then over on the left side of the screen, you'll see historical data, and you'll also see what we call analytics, which is the startup of trying to interpret what these basic readings means in terms of your pollutant exposure, your health, the amount of CO2 relative to VOCs that your house has, and interpreting what that stuff means.
Cool. Thanks a ton.
You bet.
I have a question. I read a couple of papers that said that having UV light exposure to virus similar to COVID-19, it takes 12 to 25 minutes to kill the virus. And I'm kind of assuming that your UV light is in the airflow, and as that air passes through the exposure to the UV light would be, say, just a few seconds.
Yeah, a fraction of a second. Yeah, no, that's, it depends on the power of the light. But I very definitely recommend Bill Bonfleth's webinar, ASHRAE webinar. So if you look up William Bonfleth, and I have that, let me see if, I should have that somewhere in these references, but if you can't find it, let me know, and I'll send you that link. But that discusses the dosage. It's a time and ultraviolet radiant power. Viruses are very susceptible to UV, much more so than bacteria, which are a bit larger, which are then much more susceptible than molds and spores and fungi. But viruses, so a fraction of a second is actually quite a long time relative to the amount of ultraviolet radiation input. So our bulb is about 16 watts, and you get about 25% conversion of that into ultraviolet radiant power in this 200 and some nanometer wavelength band that destroys the DNA of a virus, and at that level that it's roughly about a 85% single pass kill efficiency. Okay, so and then as you're recirculating it, you're going to take more and more of that out, which in the analysis that I did, showing how the probability of infection drops with a filter, which a filter, as it pulls, say, 80–90% of particulates out, that 10% then recirculates through, and another 90% of that gets pulled out, and then it goes through, and another 90%. And similarly with UV as it passes through. Another unique feature, though, of our setup is that our UV, we purposely designed our ducts 5 years ago when we developed the second gen system out of aluminum and made provision for ultraviolet, which we've been testing over the last 3 years, and it's just coincidence that the pandemic hits at a time when interest in UV then picks up because of that, and that we had finished our testing. And in terms of our testing, the thing with UV is that it destroys everything. I mean, you don't want to look at UV, you don't want it on your skin, and it just, polymeric materials, caulk, sealants, things like that, that we'll see it within our system. We had to be sure we weren't destroying those things. And so we ran a year to 2 years of continuous ultraviolet exposure in the CERV just to make sure we weren't destroying the unit. But at the same time, that bulb then is going into an aluminum chamber, aluminum ductwork, and then our coils, our heat exchanger coils, are all aluminum. And that gives a multiplier effect, and you'll see this in Bonfleth's webinar, of about 75% over just a bare bulb going into air. And that's because of the re-reflection of it. Aluminum's about 90% reflective of ultraviolet, where galvanized steel is like 50%. And so we haven't done our own microbial studies. These studies with viruses take very specialized, even with a safe virus, facility in order to run a virus through something to then to culture it. It's different than culturing a bacteria. You've got to culture it in cells, and the handling is very difficult. So we're going on other people's data, like EPA, who did some of the original work, and then some ASHRAE test work. And so we're basing it on, on those levels. But But a fraction of a second is more than enough to substantially kill a virus.
I have a CERV-1. Do you have the UV that you can put in that?
Yes, so on the CERV-1, the same UV bulb you can acquire from us, and then you would mount it in an external duct. And so downstream of the CERV, so the air would go through your CERV and get filtered, and then as it goes to be supplied to the room, you'd go through a length of duct, maybe 3 feet or so, and we'd recommend aluminum duct with this bulb inserted into that ductwork. So maybe an 8-inch section, 8-inch diameter section of duct with the UV inserted in that. And then it's 16 watts, which can just be plugged in directly. And the bulb just runs continuously.
Okay, thank you.
Yeah.
I have a question. I just had the CERV-2 installed a couple months ago, and it brought my CO2 levels down from about 1,000 ppm to around 500 ppm. But I find my VOCs, they skyrocket, especially when there are wildfires nearby. And even with the VOC set point hit, the CERV doesn't seem to be able to bring the VOC down. Do you have any recommendations about how to handle when there's a lot of VOCs outside?
Not yet. This is a problem in the West Coast, the Intermountain region where you are with forest fires in Vermont. It's often a neighbor burning wood because wood is very plentiful in Vermont, and so when your neighbor's upwind from you, that blows toward your intake. And so we're working on that, and for the time being, when you have that situation, it's best to disable the VOC sensor now and then operate on CO2 monitoring. But when you do have that outdoor situation, in addition to, say, the MER 13 filter, you can also then add, a carbon impregnated filter that we have. And that, if there's odor coming in because of that outdoor fire, that will absorb that part of it as well. But we are also, we haven't put the algorithms in yet, but the CERV-2 is set up so you can have both inside and outside CO2 and VOC measurements. VOC measurements outside, the idea is that as those go higher than VOC measurements inside, that then we wouldn't control on VOC outside. But we're studying that because it's a tricky thing. We also see situations where you're in a nice pine forest and you're smelling the terpenes and pine forest smell. That is that healthy or unhealthy? Even though I don't know if a pine forest smell is healthy or unhealthy, I know I get positive thoughts when I smell fresh pine forest. And there's also a placebo effect when you smell something like maybe baby powder, which is harmful as a particulate, but pleasant thoughts. Well, I think a lot of us have pleasant thoughts when you think of babies and things like that. And that's a very powerful thing in your mind when it's on the positive side of things. A religious ceremony with incense. Benedictine monks, which are immersed in incense, have, of any population group, one of the highest levels of longevity. So there's a lot of confusing things out there, but we're studying that. And the nice thing about the CERV is that we can broadcast out as we put those new algorithms in place, those features as we put, say, more active outdoor VOC monitoring with indoor, or as we link into air pollution reports for a given region, or as we have a whole neighborhood of CERVs and you may have seen some other sensors like the purple sensor and that can kind of locally define polluted areas and less polluted areas of a city, because what's happening at the airport isn't what's happening in your neighborhood. So there's a lot of things coming along the line, and just stay tuned. We're looking toward implementing those as soon as we can.
All right, thanks a lot.
Mhm.
Well, thank you, Ty.
Yeah.
And I might add that Norbert and I can install the UV lights at any of the CERV-1s or 2s in that neighborhood. And any more questions? See, one other thing I thought of when Larry asked about energy is on a 6-inch, your 6-inch fans on the CERV-1, I think I'm averaging about 70 watts per fan, but you can raise and lower those things, so that makes it hard to calculate. And then your heat pump will automatically vary its RPMs and raise and lower its wattage. I've monitored mine from 500 watts down to 212 watts, depending on the energy it can get outside. It'll adjust to that. So it's you can't judge the CERV on its energy consumption. It's all over the place.
Yes, very definitely. Like any heat pump, for example, in the winter, without changing the speed of things, the colder it gets, the less power the compressor draws, but the less capacity you get. And somewhere around, say, -10, -20 Fahrenheit, essentially the electric power going in the compressor is the heat that you're getting out of the CERV. Yeah, COP-1, yeah. And, but still, we don't want to sacrifice fresh air. And so, but, another thing, as it gets more and more wind, which often is true in the winter, even in a sealed passive house, the higher the wind speed, the more of your air, and even though we do want to minimize what comes uncontrolled through cracks and that, it's a reality that it does come through cracks and things. And that you may get most of your fresh air from wind blowing through infiltration, exfiltration. And the CERV modulates so that if, say, half of your needed fresh air came from, because it was 20, 25 mile per hour wind, the CERV doesn't have to run that much in fresh air mode. It's in recirculation mode where it's contributing heat on top of whatever heating system you have. And so that's, part of what the smart ventilation is doing, as well as automatically adjusting relative to occupancy and occupant activity levels.
John, could I chip in a little bit? First of all, Ty, I've studied your website and I've listened to you many times, but I'm always learning a lot when you're coming, because you are such a dynamic player in this field. I have one simple question, and that is, I like to ventilate my house to the minimum of CO2 during the day when the sun is shining, so I'm bringing in fresh air outside without even heating it up. Is there a possibility to actually put some timing on the CERV function, like to say, okay, between 12 o'clock and 4 o'clock, I would like it down to 600 ppm, and at night I would like to go up to 850, so that I can actually bring an extra energy saving feature into the machine?
Yeah, I'll tell you that that's an absolute certainty that we're actively working on that scheduling type feature. So if you think of Ecobee and how you schedule on like an Ecobee thermostat, you'll have that capability, and that will get broadcast out.
So there's a schedule for this, the time schedule?
No, I don't. I'm low on the totem pole as far as.
Okay, making these decisions.
Yeah.
Okay, thank you.
Yeah, but we want to hear from folks about. I mean, that's a lot of the features built in have been from comments like that, and as we hear more and more from folks, that drives us to put that in. I mean, it's really a matter of us finding out what's missing or what would be beneficial, and so hearing that is very valuable to us.
Perfect, thank you.
I have a question. Yeah, I put some questions into the chat box. I don't know if they showed up or not.
I'm not very proficient at looking at that, William. Let me see if I can,
I can read you the questions.
Yeah, why don't you do that? Because I'm likely to cancel the whole smear here.
Okay, because the three questions I have is, one, can you recommend a book or two on this subject? And then I can read the other questions, but maybe you want to answer them one at a time?
Yeah, so as far as the book, it's really lacking. As good as ASHRAE is in materials like the ASHRAE Handbook of Fundamentals, residential isn't addressed, and then the things on air quality aren't addressed anywhere. But so of course I'm biased, but the best source of information, which is not an advertisement for the CERV, but if you go on our website and under what's called multimedia, the multimedia bar, you'll see publications, and under publications, you'll see 2 reports. And again, these are not CERV-centric, but they're on smart ventilation and then on smart air distribution. So it covers in depth a lot of the things that we just superficially talked about here.
Okay.
And on top of it, you'll find some additional reports, 2 reports on duct design and how you balance the economics of the fan power that it takes to blow through a duct versus the size of the duct. Bigger ducts cost more, but you have less fan power to blow an amount of air through. And then also on how you test ducts to make sure, in the field that they're operating properly. And then let me mention a couple other reports. There's a series of 4 reports on latent loads. And William, where are you located?
Centennial, Colorado.
Oh, okay. So latent loads aren't too important for you, maybe a little more on the dry side of things. But those 4 reports talk about how we generate moisture and sources of moisture in a home, and then climate-related moisture issues, including Colorado, but all around North America. And then how different machines, from heat pumps and now today's heat pump water heaters, and then the CERV, how those actively manage moisture, and then finally putting that whole ball of wax together. And then the last thing I'll mention is that there's a report called the Vermod report, VERMOD, and this is a report we wrote based on 1 to 2 years of data collection on 13 identical manufactured homes that are occupied by very unidentical, we like to tell people they're exceptional, that everybody's exceptional, but very exceptional people. So from the same home with 1 person in it versus 5 people, all different aspects of how they like to control comfort, air quality, and then the energy efficiency of those homes, from the microwave oven to the clothes washer, and hourly data collected from a year to 2 years for these homes. But it's the most detailed report I know of as far as indoor air quality, comfort conditions, and energy. And if that's not enough to put you to sleep, let me know, and I can mention some other reports that should do that.
Okay, so those links to those are all on your website?
Yes, yeah, you can download, those are all PDF reports you can download.
Okay, so that, I think kind of, because the other two questions was, you probably, your website answers these, is one is, does your company offer an application book on this subject? I know hard copy is kind of old fashioned, but that's kind of what I think in terms of. And then the second question was, so if I wanted to search for information on these concepts to study them a little bit more, what keywords would I use? And the final thing is, I live in an existing house. I'm not going to scrap it and put a new house in place that incorporates all these features. Oh, and the retrofitting of features is really a big issue for me, and I think probably 90% of the country.
Yeah. Oh, yeah. You're absolutely right. Retrofit is the big dog, where new construction is maybe 1% of housing a year. That a home lasts 100 years, so about 1% of that gets replaced. That the much bigger and really more significant market as far as improving our health is in the retrofit. One thing you'll see in our newsletter, a couple of articles written by Alex Long on his 101-year-old house, where he ripped out, he's now fossil fuel free, ripped out the gas furnace and the old air conditioner, installed a CERV-2 heat pump water heater, a real nice ream unit, and then two 1-ton mini split heat pump, ducted mini split heat pumps. And so that should be a nice example of that, but we're seeing more and more renovation going on. Let me mention as well, I'm glad you brought that up. If you go to buildequinox.com/zeros, ZEROS, and if you don't find that, just send me a note and I'll send you that link. But we have free design software. It's online, free to use, like PHPP, like other design software. But this is software that we use in our own analysis and research, but it's been made so it's very simple to use. And we've got people all over the country using it. And there's some material with it to get you started, but you should find that you take a look at, a lot of it's going to make sense, and any questions, let us know. But that design software we call Zeros, we have what's called 7 steps to net zero design. So there's a handout when you go to that link, buildequinox.com/zeros. And that includes the economics, it includes the financial, it includes the solar, it does the latent, which still in passive house, it's very rudimentary, if anything, as far as how latent loads are determined. And I can tell you that, a passive house in Minnesota has a lower load than a passive house in Miami, because of the latent load significance in Miami. And so latent is critical to incorporate, and it's not getting incorporated yet properly. But that Zeros will give you an ability to do those calculations, and it will also model ERVs, HRVs, as well as the CERV, a demand control ventilator. And so play with that some too, and that'll let you, whether it's retrofit or new construction, let you compare different design options and their costs.
Great. So your website essentially has a bibliography as part of it that lists the references you make, right?
Yeah, and we're trying to figure out how to organize this in a manner as you've described, so it's more educational and what form that should take. But my background is I'm an educator. I'm an old retired professor, but to me, the most maybe important thing we can do is just help educate others so it gets promulgated and moved out, so people have these design tools and understand the cost and effectiveness of air quality, water usage, energy usage, comfort, and all these things.
Yeah, it sounds like you have a real strong message and collection of information to deliver. I enjoyed your presentation very much.
Yeah. I'm like a broken record, and my wife has to listen to this every day of her life. So
There's worse.
One last point, Ty, is many people ask about controlling their mini split from the controls of the CERV, and your recommendation for that? To do or
John,
not?
you're breaking up a little bit. I think you asked about the CERV controlling like a ducted mini split.
Yeah.
Okay, yeah. I mean, this is real exciting development as we, and you'll see a few newsletter articles from about January, February this year. We're looking to actively control comfort conditioning systems of various sorts, and we do in a number of homes, but to make it kind of Apple-like where things seamlessly plug in together. And so if you're using a Mitsubishi 1-ton versus a Fujitsu 1-ton mini split, or you have an array of them, whether multi-head or individual, we've developed the technology so the CERV can integrate those controls. So unlike an entertainment system with a controller for your TV and your sound system and your tuner and this and that, that the CERV is home for managing all of those devices. And so, you know, just to maybe a peek at the future, that the near future, if you have multifamily, we see a small package of the CERV, a ducted mini split directly mounted above and directly ducted into the outlet of the CERV. So the CERV does the air quality and the filtration, feeding into the ducted mini split, which then gives you the bulk heating, cooling, and latent conditioning. But the CERV is in control of the mini split. And you need to know the basic operation of the mini splits to get the best efficiency. If you keep the mini split in what they call stage 1, heating or cooling, you'll gain about 30% efficiency, as opposed to a controller that, say, might alternately go into stage 2 and then back to stage 1 and back to stage 2. And so we've been studying these, and we've released the controls for that, but we're just building that area up. But at the same time, the CERV can control multiple mini splits through both wired and wireless control. And so if you're in a 10,000, 20,000 square foot space, the CERV might, well, it would be the brains to manage the air quality. And then if for some reason it was a space that was going to have a lot of people, it might bring in a bigger bulk fresh air unit that might do 1,000, 2,000 CFM of fresh air. And on top of that, do a half a dozen or a dozen mini splits. Or if you think of a multifamily, one CERV could manage, say, 2 apartments or a duplex, and it divides its time up, keeps the air totally isolated and separated from one unit to another. But in that case, that the units can have smart ventilation at a more economical cost, and then each one could either have its own mini split to do its own comfort conditioning or share. It's nice, though, if they're independent, just because we see situations where somebody likes their house 85 degrees and somebody likes their house 60, so this house is cooling while this one's heating. And with a single comfort conditioning system, you can't do both at one time. You could alternate, but you lose some efficiency and some flexibility that way. But there's a lot of exciting things coming up, and we just see it as a whole new playground that we can integrate in. And with the CERVs over-the-air upgrading, that we can broadcast out these features that a CERV never goes redundant or you know, so we keep them up to date.
So you brought up one other item, Joyce, right there, and that is the CERV has a high airflow capacity and it's expensive. So if I have a 700 square foot apartment, I can maybe split one CERV between the two based on smart dampering controls.
Yeah. Yeah, very definitely. Yeah, we've shipped units out for doing that, and we haven't written anything up directly about that. But yeah, we have, you know, where a home that then has a small apartment, and so you can divide up, maybe this one gets 30% of the serve time, this one gets 70, but then there's situations where maybe this one's polluted and that one isn't, so it can borrow time, but it can never steal time, versus a multifamily where just two similar apartments, say studio apartments or something like that. And then,
No.
Yeah, and there's some exciting things coming up too, where with us controlling the comfort conditioning, let's say as you get into a 100-unit apartment, and in places like California where demand control is very important, the cost of electricity is very significantly impacted by the time of day. That if you think of one unit just talking to the utility and doing its thing to manage that load, but now think of 100 units that can communicate with each other either through a combination of local wireless as well as through the internet, but that they can coordinate how they're doing the conditioning of those apartments in a way that's fair and equitable, but also that overall lowers the demand on the utility, and that could be a neighborhood as well. It doesn't have to be an individual building, but some real exciting things on that side that will benefit the utility as well as us through lowered rates and costs.
Well, if there aren't any more questions, go ahead.
Yeah, so just, I don't know, I'm not clear on stage 1, stage 2, and mini splits.
Yeah, so in most heat pumps in general, whether they're called a mini split or not, they'll kind of have a stage 1, which you might think of with variable speed compressors as running at half compressor speed, and then stage 2 would be running at full speed. But even in those stages, there might be some variation of the compressor speed. So for example, with a mini split, usually they'll limit the output temperature. In heating mode, they might go up to 120, 130 degree Fahrenheit output temperature. And if the airflow is such that it's hitting 125 degrees, and that's its upper limit, then it will start winding the compressor down in capacity until that temperature drops down. But stage 1, stage 2, when you wire in a thermostat, you'll see like a Y1 and a Y2 for yellow wires, and that's stage 1, stage 2 cooling. And you'll see a W1, W2 wires in most thermostats, and that's stage 1, stage 2 heating. And then smart thermostats will say, go to stage 1 heating first, and then look at the change of room temperature toward your target temperature. And if it's taking too long to get there, it'll go up to stage 2 heating. But if it's even smarter, it may see that, well, it might be longer than, say, what the algorithm set up for, but it is making progress. Why not wait? Because when you're running the compressor at half speed, there's a large efficiency gain running at that lower capacity. And it's kind of, when you run So your standard old-fashioned air conditioner without speed control, that would run on a duty cycle, say a bang control. It's 100% on for say 50% of the time and 100% off. And when it's 100% on, there's a lot more inefficiency with supplying twice the capacity that's needed for half the time than there is for supplying just the right amount of capacity for 100% of the time. And so this is what you get out of out of the multi-stage heat pump control.
Okay, that's what I'm struggling with in smaller passive houses. It's very hard to. The loads are so low that I'm working with Mitsubishi almost exclusively.
So, I think from a February newsletter, you'll see a thing on mini split control that talks about this. But one of the interesting things that's in the opposite direction, so while a lot of our passive house friends want to get down to this little tiny machine, and actually from 2 years ago, you'll see an article called Mini Split Madness, and I think in our publications there's a report that goes into depth on mini split operation and costs and things like that. But if you look at, for example, Mitsubishi's half-ton, three-quarter-ton, and one-ton mini split, it's the same freaking machine. It's different algorithms. And you look at Fujitsu's 9,000 BTU per hour and 12,000 BTU per hour, it's the same machine. It's just the algorithms are different and the compressor control is different. There might be a little bit different compressor capacity, but if you look at the dimensions, and I've taken them apart and just verified it's the same heat exchanger, it's the same everything in it, it's just the algorithm in it. And you'll see that the 6,000 has a little bit better performance than the 12,000. And that's really because it's just running at half compressor capacity. So what this means is that if you have, say, a design capacity of 1 ton, and you would say, okay, let me just put in one ton mini split heat pump. If you put in 2 1-ton heat pumps and you control them properly, okay, two independent mini split units, you will get 30% better performance because those 2 mini splits will operate in stage 1 instead of kicking up to their higher stage heating or cooling. So this is in the opposite direction where people are thinking, oh, I want to get down to a 6,000 BTU per hour. No, get the 1 ton. So you've got that capacity, and most of the time it will modulate down very efficiently to 6,000 BTUs per hour. And then when you have a party and you're cooking spaghetti and people are dancing or whatever, and you need a ton of cooling because of all of that load, not because of climate, you'll be very thankful you've got that. And if your house is a little bit bigger, but again, still maybe just a 1-ton design load, if you put in 2 independent mini splits, so they're operating 6,000 BTUs per hour rather than 1 operating at 12,000, you're going to gain significantly in energy performance by having those 2 individual machines. And then you gain better comfort zoning, say an upstairs versus a downstairs, or this side of the house to that side of the house. And you'll also get a redundancy so that if this machine's down, you still have this machine. And in a passive house, as you know directly, it really doesn't take much of a load to keep it in a comfortable range. But it's kind of an opposite direction of thinking.
Yeah, the challenge of this clarifies a lot. I mean, the challenge of short cycling is what I'm up against. And the other part of the challenge is that, cost. So if I can put 2 interior heads on 1 exterior unit, the variability drops substantially, and that's I'm struggling with all these issues.
Yeah, and so that's another excellent point. With the multi-head, now what we've seen and in passive homes that we work with, we'll recommend two individual mini splits rather than the multi-head, because we haven't seen much of a cost difference between, you do have the cost difference of a second outdoor unit, but often you're putting in the capacity of two individual outdoor units with a single bigger one. And then you've got the manifolding and the controls. And so we haven't seen too much of a differential cost that way. So for example, two individual ductless mini splits might be $1,500 to $2,000 a unit. And maybe the multi-head with two heads might be $3,000, $3,500, somewhere in that range. But you gain with the independent ones that this one could be in heating and that one could be in cooling, which doesn't happen often in a house, but we've seen where the basement might need a little bit of heat and the upstairs might need a little bit of cooling. And with a multi-head, they both have to be in the same mode until you get to commercial units that have what's called a three-pipe system. You don't have the ability to heat this head and cool this head. And so you get that independence as well as that efficiency gain by having more capacity, allowing you to run more in lower stage conditioning. And then they'll wind down about 3 to 1. So you'll get down to maybe 3,000 BTUs per hour in a 1-ton machine.
Wow. I'm glad you recorded this. I'm going to have to listen to that.
Now I have to hold to it. Well, if I were a politician, I guess you could record anything.
No, it's a lot to absorb on my part.
So, but look up that report, Mini Split Madness, in that article, and that's got a number of those details. And
okay, thanks.
So Bob, I'll add some real world numbers. I have this Carrier 42 Seer, and it seems to have three levels. It's usually in winter time putting out between 90 and 105 degrees on the low zone, and it's pulling between 200 watts and 500 watts. And then if I turn up the thermostat, it goes to a mid zone of putting out maybe 120 temperature, and it's pulling between 500 and 1,000 or 800 watts. And then when I put it up to 85 degrees, its max, it runs right up to 1,900 watts, the maximum of the circuit breaker. And that seems to be a three-level heat pump. And I'm very impressed with it. The 200 watts heats at 98 degrees, is cycling on and off and heating my whole house because, of course, I'm R55 walls, and
Right.
it doesn't take much.
Okay, well, we're up against the low load conundrum, and I haven't. This is really brilliant PE. Beverly, oh God, I can't remember her last name. Anyway, she helps the Passive House community, but hasn't said much about this. This is very interesting. Interconnecting CERV-2.
is that maybe Kimberly with Mitsubishi?
Yeah, Kimberly, exactly.
Yeah, she's excellent. Yeah, very knowledgeable.
But this is, I haven't heard this from her, so this is very useful. Thank you.
Anyone else? Well, I really appreciate your talk, Ty, and we'll look forward to some of your upcoming new inventions.
Well, thank you very much for hosting, John, and thank you everyone for attending. Have a good day.
Thanks a lot, everybody, and we'll close this down.